Okay, so I hope you're clear with the concept of standard deviations. Now we talk about empirical rule. Now, again, this is based upon the variation in the data, how much the data is spread around the mean, and that spread actually indicates the percentage of data values within a certain range. Okay, so let's talk about empirical rule. Later on, we will talk about this, that why we call it empirical rule, but let me indicate here that empirical means through observation, that we have gathered from observation. So over the years, statisticians have, seen that when the data is symmetric, when it is bell-shaped. Now, whenever we say that data is bell-shaped, that would be meaning that the data is symmetric or it is in the form of normal distribution. And what does that mean? That the mean, median, and mode, they're in the exact center of the mean data. And on both sides, you have 50% data. Okay. So for the data which is symmetric, bell-shaped, the standard deviation has the following characteristics. So we have a histogram or a polygon, maybe in this shape, where we have y-axis here and x-axis here. The data which falls between certain range is like this, that 68% of the data falls within one standard deviation, and 95% falls within two standard deviations, whereas 99.7% falls within three standard deviations. Okay, here is a pictorial representation of this empirical rule. As you can see, that this is a symmetric distribution. Why this is a symmetric distribution? Because at 0, you can see there is the mean of the data, and on both sides, there is equal number of values. So if we extend the variation of the data to one standard deviations, so you will see that there is exactly 68% of the data within one standard deviation, 34% to the left of the mean and 34% to the right of the mean. If we extend it further, 95% of the data exactly falls within two standard deviations, and 99.7% would fall in three standard deviations. Okay. Of course, the remaining data is beyond three standard deviations, but most of the data falls in three standard deviations. So this empirical rule at certain times will be very helpful in order to find exact values within a range of data, right? And so how can we use this empirical rule? For example, if the mean value of homes on a street is $125, $125,000 with a standard deviation of $5,000, the data set has a bell-shaped distribution estimates percent of home between $120,000 and $130,000. Okay, so we have all the information. We have the mean, first of all, then we also have the standard deviations. So what is the mean? 125. And what is the standard deviation? 5. So you can see that we have to find out the information between 120 and 130. And both of these values, they are only one standard deviations away from the mean. Why? Because mean is 125,000 and the standard deviation is 5,000. If you add one standard deviation of 5,000, you get 130,000. If you deduct that, you get 120,000. So as I told you, standard deviation is always positive as well as negative. So one standard deviation actually has 34% to the left of the mean and 34% to the right of the mean, in total 68% data. So this blue area has 68% data. So if we try to estimate the percent of home between $120,000 and $130,000, they're exactly 68% homes. Okay, so you can see from this statement that 68% of the houses have a value between $120,000 and $130,000. Now, what if the data is not symmetric? What if is in any other shape? Then what we got to do? Can we apply some rule that can give us the information that what number of values fall between two certain values between a particular space? Yes. So one of the statisticians called Chebyshev actually came up with this rule, which is 1 minus 1 over k square, where k is the number of standard deviations. Okay, so we're going to see this. Yeah, let's see. So k is basically the number of standard deviations, and there is one condition here that k needs to be more than 1. There should be more than one standard deviation in the data. And then we can find out how much percentage of data falls between two values. So for example, if we want to find out how much data falls within two standard deviations, then we have to use k as 2. So 1 minus 1 over 2 square is equal to 1 minus 1 over 4, that is 3 over 4, and that is 75%. Again, you can try using 3 in place of k, using 4 in place of k, and you will come up with the answers. Okay, here is an example. The mean time in a woman 400-meter dash is 52.4 seconds with a standard deviation of 2.2 seconds. At least 75% of the women's time will fall between what two values? We can easily calculate that. First of all, identify where the mean falls. Okay, the mean is 52.4. Okay, so how much actually values fall in within two standard deviations? Again, we have the formula 1 minus 1 over k square. Since the standard deviations are 2, so what can we do? We can put 2 in the place of k, and we will find out that 75% values fall between the range of 48 and 56.8. Right? So if 52.4 is your mean, and you want to add two standard deviations, then you multiply it 2.2, which is the standard deviation, with 2, and you add that to 52.4, and the answer would be 56.8. Again, if you can deduct that from 52.4, the answer would be 48. Right? So this is the range between which 75% of the values fall. Right? Again, as I told you that for group data, we have to modify our formula. And here is a formula for the standard deviation of the group data. And you can see that we have the midpoints that we deduct from the mean, and we square these deviations and we multiply them with the frequency and divide by n minus 1. Of course, whenever we use group data, we are basically working on a sample, so we will use S. S is the denotation for sample standard deviation. All right, so here's an example. You have classes, you have their midpoints, and you have frequency. You deduct the midpoint from the mean of these classes. And remember, we use this formula to calculate the mean of the grouped frequency, where midpoints were multiplied by frequency and they were divided by n. So after finding the mean, you deduct the mean from the midpoints and you get these products. Then you square them because these are deviations, and you get to the sum of squares after multiplying each deviation squared with frequency of that class. Right, so this is our sum of squares in group data. And then we divide that with n minus 1 to get to the variance. And when we take the under root of the variance, we get to the standard deviation. So 10.2 is the standard deviation for this group data.